Hello, this will be my weekly recording for week 1 for chemistry. So the first question, the question is to derive the equation of bond enthalpy using any chemical reaction. Well, when bond enthalpy is basically the energy that it takes to turn the reactants to the products. So in this case, it's from N2 and 3H2 all the way to 2NH83. Now, this is calculated by in order to calculate this, you have to think of a Lewis diagram or that shows the bonds of the reactants and the products. So for example, for N2, it will be a nitrogen with a triple bond with another, which is a diatomic atom in a gaseous state, and hydrogen, which forms a single bond, which gets turned into a reverse reaction, but gets turned into 2N with bonds to each hydrogen atom. Now, one thing to notice is that the equation, it has, because it's a calculation of enthalpy, and the bond enthalpy is defined as the amount of energy needed to break gaseous bonds in 1 mole of the 1 mole. We have to put it into a gaseous state. So that's why they're all gases. Now, as I said, in order to calculate the bond enthalpy, basically initially what we have to do is that we have to break all the bonds in the reactants. This triple bond between nitrogen, there's 3 moles of hydrogen single bonds, and we have to break them all apart, and then we have to put them together in the form of 2 moles of NH3. So let's first see this part. Here, you can get the data for breaking all these bonds from section 11. Section 12 from the data booklet of 2025. So in this case, it was a triple hydrogen bond, a triple nitrogen bond, gave you a 945 kilojoules. Now, here is 945 kilojoules. Now, this unit is in kilojoules per mole, right? So, but since this is 1 mole of the substance in this reaction, you can just multiply by 1 mole, and then you get this. And that falls for this, where in here, for the H2, there is 3 moles of it in the reaction, for 1 mole of dinitrogen. So, in this case, it will be 3 multiplied by, what's an HH bond? It's 436. Now, this is the end, and this turns out to, let's pull up a calculator, of 2,253 kilojoules. Now, this is, of course, we're breaking the bonds, so we're putting energy, so it's endothermic reaction, so endothermic, so this is always positive. And now, let's look at this. When you make a bond, it releases energy. It is exothermic. That means that the change in enthalpy is below 0. So that means that this one, for this, since we're putting all these broken atoms together, it is negative. So in this case, since it's 2 moles, is 2 multiplied by 3 NH bonds, which according to the formula booklet can be turned into 6 multiplied by NH, where is NH? Here, of 391. And if you pull up a calculator, it's 6 times 391. 691 is 2,346, but let's be reminded that we have to add a negative, so it's 2,346 kilojoules. Now, we have seen that we put in 2,253 kilojoules, and then it releases negative 2,346 kilojoules. So that means that the total net enthalpy change, so net and bond enthalpy of the reaction, is equivalent to 2,253 plus, since we're adding the empathies, negative 246. But this gets turned into 253 net minus 246, which is negative 93 kilojoules. So this will be the solid reaction. So this is showing that the reaction in a forward reaction is exothermic. This is negative, yes. But now this gives us the general gist of the equation. Basically, what we did was that we broke all the bonds, so we put in energy, and then we put all the bonds together, so we release energy. So that means that the net bond enthalpy of a reaction, let's write it in some vibrant, more vibrant color just to stand out, is equivalent to the total bond enthalpy of reactants, because we have to break them, adding the negative summation bond enthalpy of section 12, since it's always positive, of the products. Now this gives us the equation of sigma BER, the bond enthalpy of reactions, minus sigma BE products. And this will be the final equation. This will be the derivation of the equation of bond enthalpy using the chemical reaction of N2 plus 3H2.